Do you have any doubts with our related to our yesterday's discussion? Okay. Yeah. So if you don't have any doubts, of course I am trying to put the similar points over here, okay, in a slightly different way. You can ask any doubts, okay, I mean in the similar scenario like what we discussed yesterday. So what exactly we did yesterday? Yesterday we have just summarized that generally when you say an embedded system development, okay, what will be the setup? Okay, there are possibilities like you can program separately the chip and put into the actual system, or you try to see that the system itself you can directly program there and debug, okay, into your computer back. That is what we have seen, and we discussed slightly about the history, okay, or what I should say evolution of something called FPGAs. Okay, what we are seeing today, FPGA and CPLDs. So what they are initially, I mean, and what type of shape they took over time, and what you are seeing today. So today what we shall do, first, I mean, let us go through the basic concepts of FPGA based embedded system, okay, and understand how it is different than the conventional embedded system development, okay. Then we will go in between, okay, into Xilinx ISC tool, open the what I should say the layout or a floor plan of some FPGA. We will take Spartan 3 FPGA, okay, because most of the boards what we are using here for experiment, they are Spartan 3 FPGAs. So let us see inside what is a Spartan 3 logic cell consists of, okay. You'll find quite similar things but a bit more complex things because they are modern FPGAs and all, okay. Then we will talk about something called Pico Blaze, okay. Pico Blaze is an 8-bit microcontroller core, okay, which sits on FPGA. That's what. Tomorrow's talk will be based on Microblaze, which is a 32-bit microprocessor core on FPGA. You'll come to know, don't worry, what is a core, all these things we'll discuss, okay. So basically what I want to say, the FPGA based embedded system development will have this kind of setup. Is it quite similar to the conventional embedded system development? It is quite similar. The difference is, in a conventional, let's say microcontroller based system, you will have a microcontroller based board here, correct? Or maybe if you are developing an ARM based system, ARM advanced RISC yesterday we have seen RISC machines, okay. So anyhow, that is one type of microprocessor. So I'll have ARM board here and there will be IDE for it, okay. Similar, quite similar. In any embedded system development, you will find this only, okay. Now, so yesterday we discussed about it, but now I am putting in a more formal words. I think we have not discussed these aspects earlier. Did we discuss these aspects in our VLSI course? We have not discussed, no? We discussed about what is called VLSI perspective, semi-custom VLSI and different categories. Okay, now so it is not repetition for you. See, embedded systems can be classified based upon the complexity of the thing, isn't it? The complexities, different complexities, okay. So these are very simple to understand, so I don't spend much time. You can see the examples, you have simple embedded systems where the small alarms or timers, they are also embedded systems only. In fact, medium complexity embedded systems, they involve generally a microcontroller, okay, or a small processor, maybe a small processor which is doing some basic job. Like examples, if you see remote toys, okay, mouse and keyboard. See, mouse and keyboard, they are coming into class of embedded system. But the system which you put together, mouse, keyboard, CPU, monitor, that is not an embedded system. That becomes a general purpose system, okay. But mouse by itself is an embedded. If you open the mouse and see, generally, definitely you will find some kind of microcontroller inside there, because it is doing some kind of job. It is, if I talk about the optical mouse, what we are using today, okay. So it is getting data from some optical sensor, isn't it? And it is giving into the motherboard in some form, electrical form, okay. So like that. Now large complexity embedded systems, when you say, generally, like yesterday we were talking about, you can have an embedded system based upon microcontroller, you can have an embedded system based upon microprocessor as well, isn't it? So whenever we generally go for microprocessor based embedded system, it will be generally complex, okay, than microcontroller based, isn't it? See, whenever your requirement is only reading the data from some sensors and updating to some other sensors or some other ports, microcontroller is well suitable, okay. But let's say I have some requirement where I am not only reading the data and writing the data, lot of processing is involved. We obviously prefer microprocessor based embedded system. So today, if you see the majority of the embedded system which are coming with the ARM processors and all, okay, they are all actually comes into this category. That's the reason the first example what I put is a cell phone, isn't it? So cell phone, if you see, I mean, if you try to draw a block diagram for a cell phone and try to describe its major functionalities, what you'll find for a cell phone, of course the cell phone will also have some analog part, definitely there will be antenna will be there, antenna front end will be there, then you digitize that and do something. Okay, so there is a keypad which is like one input device for you. Okay, so this should be processed some way, isn't it? And I generally do for some some algorithms, some modulation schemes, demodulation schemes are also running in that. Okay, some protocol also running, maybe GSM or CDMA protocols are all running inside. So it is quite complex embedded system. It is not so simple. Okay, not only reading the data from X keyboard and writing data into microphone and all, loudspeaker and all, a lot of processing is done internally. Correct? You are doing demodulation, some kind of demodulation. Communication people understand. Modulation and demodulation are not so simple, isn't it? So a lot of processing is involved. So that's the reason they are put into the class of complex embedded systems. Okay. So, and another thing is like when you have a big industry, data acquisition system you are talking of, that is also complex. Network routers, they are good examples of embedded systems. You see this size box, router, or maybe some broadband modems, they come with a router inside. Okay, so something like that. So they are also complex embedded systems because they have to take the data, okay, through one packet. So internally some kind of switching has to be done. There is some different layers are there in TCP/IP. Okay, so different routers are also there. So a lot of mechanism is involved inside the router also. Okay, that's also not so simple. So like that. Network switches, of course, there is a difference between router and switch, lot of things are there, but that is also one network device, okay, which is required when you are connecting several machines over networks. Now let us go to the last one, okay, where FPGA can really be suitable. Okay, now extremely complex embedded systems. When you talk about these things, so generally they involve not only if you talk about cell phone application is limited. Okay, its scope is limited. Okay, once you design for one protocol, as long as you are running with the same protocol, let's say you are talking about some 3G mobile standard, some specific CDMA scheme. So as long as that is like that, there is no great change in that. Okay, but when I talk about some kind of embedded systems, let's say onboard missile controller, okay, or onboard satellite controller, okay, are you talking about flight control system in a aircraft? These kind of embedded systems are extremely complex. Okay, in those cases the design will never freeze. Okay, you will never say this is my end design. No, it is not that. Tomorrow let's say some kind of algorithm is improved in signal processing, I will put that algorithm, I will make my system more robust. Okay, tomorrow so let's say somebody has invented a more accurate GPS kind of system, global positioning system, I will put that because I have to locate very accurately where is my aircraft. So these kind of complex systems, they involve a lot of processing in it, and not only that, actually they require continuous update kind of thing. So exactly here the FPGAs become more suitable because FPGAs will allow you to reconfigure the system, isn't it? Today let's say I will use my FPGA for doing some kind of processing and all that. Tomorrow I got a new algorithm, okay, one of my engineers has invented a new image processing algorithm, okay, which gives a better result. So I can update it without any additional cost. Okay, so we will talk about those things. This is the conventional classification which you might have seen in any embedded system book. Now I am coming into a different class because we need to partition now the hardware and software. See now, this class of, now I am looking at a different view, basically the same embedded system. We are trying to separate the amount of hardware and the software involved in making one embedded system. Okay, see if you take some type of some type of embedded systems which may be purely hardware, there is no software involved in it, no software, almost like some alarms based upon 555 and all, it is only hardware level of design. You design appropriately the registers and capacitors to achieve your duty cycles or whatever the time or delays and all, that's all. So there is no software involved in it. Generally they are very simple embedded systems. Okay, now when you talk about embedded systems with more hardware design and less software design, okay, there are examples like if you have a simple data acquisition system which is based upon a microcontroller, you take data from a thermal sensor, analog digital converter, through microcontroller port I read it, I do some processing, I give that information to a computer for displaying onto some GUI, or further I take some action, let's say the temperature is going beyond some range, then I will try to control another relay. That relay is nothing but controlling the power supply to the heater, let's say. That's how I achieve the thermal control, let's say. So they are generally simple embedded systems where a bit more hardware is there, relatively if you see. Okay, software design is relatively less. I may write only 20-30 lines of assembly code, hardly. Reading the data, isn't it? You have seen the examples, how we can read data from a port, this kind of things. Okay, so it's quite simple. Now if you come to this one, embedded systems with both hardware and software design, example is a cell phone as you see. So in a cell phone, lot of hardware design issues are there. Okay, I know how I should know how to interface the analog digital converter to the processor. Inside the processor, lot of things. Processor requires an external memory, maybe RAM or ROM, this kind of things. So everything is required. Similarly, the software is also required. I should know how to write the protocols, interface, everything like that. So these are the things. If you come to this one, embedded systems with off-the-shelf hardware and more software. What do you mean by that? Most of the hardware we don't design, we try to get the hardware which is readily available there. Majority of the effort goes in actually building the software on top of it. Okay, so why we are focusing more onto this area. Okay, FPGAs are suitable, either here or either here. Okay, the latest concept today, what you see, in articles and all, people talk about hardware and software co-design. Okay, hardware and software co-design, basically that is coming into these areas. Means you are trying to design the system by designing the hardware and software together, but it is not just like designing a microcontroller board and putting software. That is not called hardware and software co-design. I will tell you what is it. Okay, when you say hardware and software co-design, it is not that you design the microcontroller board and put software on it. That is not hardware software co-design. That is people are doing almost from last 30 years. Correct? Hardware and software co-design is something else, which comes mainly in the context of FPGAs and DSP processor like that. We will discuss about it. Once we come to that point, we will discuss. Okay. Now look at that. See, why we are more focusing on this one is, whenever you are making a very complex embedded system, majority of the times we go by off-the-shelf hardware. What I mean, I'll tell you. See, for example, let's say I want to give a DSP based solution, okay, for some image processing or a voice processing system. Okay, so what we do, we generally don't try to design our own DSP board or something. Majority of the DSP boards with a variety of interfaces are given by the vendors itself. Okay, I'll get a Blackfin DSP processor along with some AD converters and required everything interface. I get the board, write my DSP code on it, use it. That is actually in this category. Okay, because see, any company or anybody, they cannot have full experience in both the areas, board design and actually the software on it. It is difficult. So majority of the times when you are going for a extremely complex embedded system, we go for actually the COTS hardware, commercially off-the-shelf available hardware, whichever is readily available in the market. We purchase the hardware and develop on top of it. Got the point? Achha, see, yesterday we were talking about DSP processors, but I forgot to mention one point. Anybody knows, when you are developing something on DSP, how do you give your software? Do you give in terms of VHDL or Verilog? Or you give in terms of C? Or you give in terms of assembly? Or any special technique is there to program DSP? You are saying MATLAB, but MATLAB is a tool, it's not a language. You are saying that MATLAB scripting should be written for doing it, like the MATLAB code? You mean to say that one? No. No. It is either C or assembly. Similar, yesterday we felt that DSP processor is quite similar to your microprocessor. Only thing is, in the design point of view, in the architecture, they modified it, okay, so that it becomes more suitable for DSP applications. So when you are developing an embedded system based upon DSP, your flow will be quite similar to your general purpose microprocessor based embedded system development. But only thing is, when I am writing the DSP processor code, I am going to use a different IDE which is designed for the DSP processor design, and my C coding and all will use the registers and counters which are all related to the DSP processors inside. Like the example, in a microcontroller, the way in which we use a T-con, S-con, which are all controlling kind of registers in microcontroller. For a DSP processor, I'll have a different flow. But the actual syntax, if you see, it will be either C code or assembly code. Now let us come to your question, your statement now. MATLAB. Yes, today it is possible that I'll write some MATLAB script, and the MATLAB script can run on a DSP processor. Why only DSP processor? It can also run on actually FPGA also. Okay, today people are talking about this technology in embedded system, which is basically called model driven embedded system development. Got the point? See, MATLAB, see, what is basically MATLAB will do, I'll tell you. Let's say you are using MATLAB to write some code, and MATLAB, you are compiling some MATLAB code, and that you are putting on a DSP processor means, the MATLAB tool in the backend, it is able to convert the MATLAB script into C code or equivalent assembly code that is placed ultimately on the DSP processor which is running. You got the point? So no DSP processor in this world will directly run the MATLAB script like that. No, because they are ultimately designed to run some mission code, again similar to your general purpose processor. So if you write the C code, the compiler, which is basically tuned for the DSP board, DSP processor, isn't it? All compilers, they are hardware specific, correct or not? Okay, see, for example, if I am using some compiler which is in Turbo C, it compiles my C program and generates some object file which is compatible to my Intel architecture, which is my processor inside. So like that, I will take the compiler, okay, which is required, for compiling into DSP board, then I will run on it. So if you are writing a MATLAB code and that is running on this one, what you call DSP processor means what? MATLAB in the backend, it is able to convert the MATLAB script to C code or the assembly for the DSP. That is coming on the board and running it. Ultimately, that is happening. Now, same thing even in the case of FPGA also. Okay, but FPGA, let me postpone that because after discussing few more concepts, I can clearly explain that. Okay, today that's a big area. Okay, people are doing it actually. Now, I mean, with using that tool, MATLAB tool and FPGA board, it becomes now actually tens of minutes of job to configure any big subsystem, because MATLAB will give a rich set of blocks. MATLAB will give CDMA block set, GSM block set, a lot of blocks it gives. Simply drag and drop what are the blocks you want, connect them, okay, configure them according to your word length, means what size of word you need, 16-bit or 32-bit word length, configure them, just generate the file, put onto FPGA, it is going to work. Today it is there, people are doing it, but of course there are some disadvantages also. Okay, we will discuss about it. Now let me proceed further. Yeah, one more important concept. All of you may note down this word somewhere, maybe as a footnote in your notebook. Cross compiler. Did he talk about it? Okay, can anybody can tell? Okay, if you know, don't note it. Okay, what is cross compiler?
The compiler is when the host is, we write a code in host, it is designed to run on some other embedded system.
Important word is missing actually. Host, correct. Use appropriate word. Architecture. The keyword is architecture. The keyword is architecture. Cross compiler is a compiler which is running on one type of architecture. I mean, which is in a machine which is a different architecture, and it is generating the code for a different architecture. Simple, isn't it? See, for example, if I use a DSP compiler in this, will it be called cross compiler? I am using an Intel machine, okay, which got Intel P4 processor, and I am using a compiler which can generate the object file and corresponding to the hex file and everything corresponding to a DSP processor. Can it be called a cross compiler? Yeah, it is a cross compiler. Got the point? What you have seen in your Microvision IDE, where you have written some C code, okay, and generate the hex file which you programmed into the 8051, is also a cross compiler. Okay, because it is lying on some architecture which is Intel, some 386 architecture. Actually, all the things what you are seeing, P4 is called 686, correct? P4 is called 686, P3 is called 586, like that. Okay, this is a standard thing, but all these are actually same. So whether you say Intel 386 architecture, they are all same, means they are downward compatible. You understand what I mean? Downward compatible means whatever is running on P4, it can run as well on P3 also. That's what I mean. Okay, so anyway, this is the idea. So cross compiler is a very important term. People talk about it. It's a very easy concept after all. It's a very easy concept. Running on one type of architecture, but it is generating ultimately a code which runs on a different architecture. That's a cross compiler. Okay. So whenever I want to use a DSP kind of developments, when I am using my computer, after all I am using some cross compiler inside, isn't it? So embedded system is going to deal with a lot of cross compilers. Okay, definitely when you are developing embedded system, most of the times you use cross compiler. That's understood. Okay. So generally this cross compiler is a part of the IDE which you generally use. So we may not see it directly, but we are using it in IDE. Okay. So now look at this. So I have brought out the issues which yesterday we discussed qualitatively in a nice form. So where FPGAs are suitable. So we have discussed now we got a broad picture. Embedded system means starting from a small toy, okay, or starting from a small 2-3 buttons which I have on my washing machine. That too, okay, a system which is running the complete aircraft. Today you have some aircrafts which got automatic pilot systems. Means if something happens to pilot, okay, suddenly you'll push one button. So autopilot. Now the autopilot system means it is going to run by itself. Aircraft will run by itself. It will communicate to the ground station. When it is landing, it will land. That's what. That is designed actually. So means starting from a small microcontroller based embedded system to an automatic pilot control system also in aircraft, everything is called embedded system. So embedded system is relatively a bigger word. Okay, just by saying embedded system, you are not telling in which area you are. So let people talk of I am on DSP based embedded system, I am on ARM based embedded system, okay, I am on FPGA based embedded system. So a lot of things are there. Okay, now we are trying to say in the complete area of the embedded system where the FPGAs are suitable. In fact, where people are using FPGAs in another way. Look at this. We know this point. Complex embedded systems whose logic required to be changed very occasionally. This is the main reason, isn't it? So point number one, it is very complex, okay, which I cannot get it done by a microcontroller or some small kind of things. I need relatively a bigger logic. Okay. Second thing is I have to change the logic very occasionally. So FPGA is very suitable. Okay. Now can microprocessor also can meet this kind of requirements? Okay. What I mean to say, microprocessor is also reconfigurable. You got my question? Microprocessor. I have developed a microprocessor based embedded system. Is it possible to change the logic what it is running with? Yes. Yes. Change the program in it. Change the program for which it is working. Isn't it? It is possible. Generally the microprocessor based embedded system will have either RAM or ROM in which the program is running. So you reconfigure it. That is possible to it. But then which type of embedded system is not reconfigurable? Microcontroller based? If microprocessor base is reconfigurable, microcontroller base is also reconfigurable. Then which is not reconfigurable? At least the VLS people should answer this. ASIC. I'm just waiting for that word, ASIC. So when you design, let's say, an embedded system in a single chip directly, okay, at the layout level you designed, you send it to the fab, got the chip manufactured, you are happy, you are running with the chip, but somebody told you change the design. Come on, once you change the design means everything should be redone, okay, lot of money is involved in doing it. Okay, so generally when you make embedded system at the silicon level, means ASIC level, they are not reconfigurable. But all other type of embedded system, microcontroller, microprocessor, FPGA, they are all reconfigurable. Okay, so FPGAs are carrying both the advantages. Okay, FPGAs have the parallel concurrent working hardware, so they are doing on par with the ASICs. Okay, simultaneously FPGAs are reconfigurable, so they have the advantages of microprocessor or conventional microcontroller based development. You have seen now. Okay, FPGAs are competing with ASICs because the way in which ASICs can parallelly do the jobs in parallel hardware, FPGAs also can do. FPGAs got the advantage of microprocessor, microcontroller based advantage thing because they are reconfigurable. Got the point. Now second thing, embedded systems where a specific hardware combination is exploited in a very small size. Now this is basically, maybe you can note down there somewhere actually, it is basically what we call as system, it is given third point, sorry, it is given on third point. So what I am trying to say is, embedded systems where a specific hardware combination is expected in a very small size. See, sometimes in a critical embedded systems, the very important factor will be the weight and the power consumption. Okay, so there is always an advantage if you can do something on chip in comparison with doing the things off chip. Do you understand what I am trying to say? My idea is, let's say I have a microcontroller, okay, I have a RAM which is outside, okay, big RAM, okay, and I have something called, maybe one analog digital converter, okay, or I have some other which is on the board, means I have taken a PCB, and a PCB I have put all these things together. So what is the interface between these all chips that is based up coming on the board, not on silicon? Got the point? The other approach is what? Take a single chip which can have a microcontroller core inside, maybe the RAM, flash, whatever, lot many things inside, let's say, then that everything you are doing on silicon. So you have lot many advantages when you are able to do everything on silicon rather than coming out of the silicon and running on the PCB. Can anybody guess the advantages? My questions are simple. What is the advantage when I can do the peripherals and interfacing on chip, on silicon, if you compare with the off chip, means on PCB? Speed, the very simple concept. When I am running on silicon, I can run with the gigahertz of clocks. People have already proved it, isn't it? People and all, they are working with gigahertz of clocks. May not be that processor clock, but I can comparatively work with hundreds of megahertz higher clock. But when I come to a motherboard, my speed is getting limited, isn't it? Okay, can anybody talk about the specification of your computer? FSB, front end system bus, FSB. Okay, any computer when you are trying to purchase, a very important characteristic, important feature for that is front end system bus speed. That is basically the clock, okay, of the data buses and all this which are running on the motherboard. Okay, today front end system buses are coming up to 800 megahertz, around 800 megahertz. Okay, means you cannot get, of course there are some techniques even you can go up to gigahertz also on this, but commercial product, when you see the motherboards and all, the clocks with which the data is moving, okay, on this motherboard, that is 800 megahertz only. But if you talk about the data which is moving inside the chip silicon, it is order of gigahertz. Got the point? Point number one. Point number two, obviously space, less area. Okay, second thing, important, power consumption, isn't it? See, the moment when I am coming out of the chip and I have to run on the board, I have to bring my voltage levels and current levels high. But as long as when I am running on silicon, there are no much losses and all. So I can as well run with the less values of currents and everything. Correct or not? So all times it is advantage. The only disadvantage may be, it is a complex to design, that's all. It is complex to design. Okay, there are more design risk or more costs involved in making the chips like that, that's all. Okay, all other things are advantages only. Power, speed, area, everything is advantage only, isn't it? Weight, everything is advantage only, that's what. So what I am trying to say is, their FPGAs are suitable. Now sir, you told lot many things and how FPGAs are doing all this job. It is possible today. Okay, today FPGAs, if you see, they are not only having the three important blocks what we discussed yesterday, but also they have a variety of blocks in them. What I want to say is, let's say for example, yesterday what we discussed, all of us we discussed something and we identified the important blocks of FPGA. What are the important blocks of FPGA? No, I'm not talking about actually the blocks inside the logic cell. I'm talking about as a FPGA, if I see what are the major blocks I see. Logic cells, you're telling inside the logic cell, that's a different issue. Okay, so logic cells, interconnects, programmable interconnect which connect between the different all logic cells and all, and I did not discuss yesterday's class, but earlier I discussed to you. You remember? I/O buffers, I/O blocks which are coming at the pads of the chip. Basically, in VLSI terminology, whatever the logic which is inside a pin of a chip is called pad. Okay, pad. So the pads which are inside that chip, basically which are reconfigurable for different voltage levels and current drives, they are also very important blocks. Okay, we will see that anyhow in the next slide. Okay, the important blocks of FPGA. They are important and they are minimum blocks. When you see some FPGA, they are there. But apart from that, today's modern FPGA, they come with a variety of features. They come with RAM inside. Okay, FPGA will come inside something with block RAMs. We will see that in Spartan 3, the block RAMs are there. Okay, FPGAs internally come with actually high-speed multipliers. Okay, they will have 18 by 18 multipliers in them. Okay, there will be some FPGAs will have 50 multipliers. Some FPGA will have 200 multipliers like that. So those multipliers can be used whenever you want to do high-speed multiplication. You got the point? See, multipliers can be realized through multiplexers lookup table like what we said yesterday. But rather than that, they put directly the multiplier logic in it, which runs with obviously very high speed, isn't it? Configuring multiplier, lookup tables and mux, that will take more time for multiplication. But let's say the multiplier, completely at the silicon level it implemented an FPGA, that obviously works the faster. FPGAs also come with a RISC processor in it. Means an FPGA internally will have a processor. You got the point? Today you have an FPGA which got 4 processors. Okay, you also go on to extent where you have 16 processors in it. Means an FPGA along with the logic cells, I/O buffers and routing channels, internally it will have 16 processors. Okay, those processors are implemented in hardware, not by writing the VHDL code and putting on top. That's a different. That is called soft processor. These are called hard processor. You got the point now? Means an FPGA capacity is equivalent to 16 processors along with the RAMs, peripheral controls, multipliers and logic cells. And logic cells can be used wherever you want to write a custom logic. You have your own logic you want to implement. You can use it. But let's say you require a processor there. Make use of the processor which is inside that one. You got the point? Today you get FPGAs which come with DSP blocks in it. Okay, DSP blocks. What are the very popular is DSP blocks? MAC unit, multiply and accumulate unit. Okay, DSP processors, you require some FFT kind of operations and all. So today some FPGAs which are tuned for DSP applications, they also come with what are called MAC units, and especially for DSP applications. You got the point? So today's modern DSPs are coming with a variety of features. That's where exactly I require this. Okay, embedded systems where a specific hardware combination expected in a very small size. You got the point? Now I'll tell you a typical example. All of us will convince definitely that FPGA is the best solution for it. Imagine a case. Okay, I require one kind of embedded system. Okay, which requires let's say 4 RISC processors doing some 4 jobs concurrently. Okay, apart from the 4 RISC processors, I am doing some decoding. Okay, which is required for a mobile application. Something I require let's say some CAN interface. Okay, CAN is one kind of protocol, isn't it? You have seen UART protocol, na? UART is known to UART, Ethernet and all. Like that, CAN is also one protocol. Okay, so CAN, some interface I need. I require the UART interface. Okay, I require, like this I require so many things. Then FPGA I can use FPGA. 4 processors what you want, use a 4 RISC processor in it. Okay, whatever the decoding logic you want, that you write the VHDL code and put on top of FPGA. Use logic cells to configure as a decoder. Okay, you write the VHDL code or Verilog code or C code for the CAN interface, put that also on the FPGA. Now you see, anything you can write the VHDL code for it and put on the FPGA. So I am getting all the variety of peripherals in a single chip, which comes this much of size. You got the point or not? So that is where exactly we are talking of. Okay, generally where they are useful, in a space applications, okay, or onboard missile onboard, where the weight is very critical, weight and the board size, okay, the board size, there we talk about. Same point I brought in a different context in a very popular word called system on chip implementation. So today people talk of system on chip. Okay, so system, generally the solution which comes like a board or a rack, several boards, you push everything into a single chip. That is possible. Today if you say system on chip, it is mostly the FPGA people are talking of. Keep in mind. Because of course ASIC also I can do. Keep in mind, whatever you do on FPGA, it is possible to do on ASIC. But only limitation is, it is costly. It is NRE costs are there, non-recursive costs are there. I can as well do the same problem for designing 4 microprocessors, okay, 4 processors, CAN interface, everything I can do. If I go for ASICs, even I get more performance also, isn't it? I get more speeds and all. Because rather than configuring the multiplexers and lookup tables to do your job, directly write the code for it. directly implement it at the silicon level. You get more speed. But the point is, lot of cost is involved. And as you know, when my complexity of the embedded system is going high, the likeliness to use more number of products will be also goes down, correct or not? See, when I talk about the toys, generally toys, when we talk, we aim at a market of millions, okay, or at least few lakhs of pieces, toys. But when you talk about onboard missile controller, will you talk in millions? No. After all, I may have a requirement of 500 missiles or 1000 missiles, or when I talk about the aircraft controller, onboard aircraft, I may require in hundreds. So, on one side, once you talk about complex embedded system, it becomes very complex. So, because it's very complex, once you want to do at the silicon level, ASIC becomes costly. On other side, complex embedded systems generally we require less in number. Got the point? Because of both these reasons, we go for generally FPGA based solutions. Okay. Now next, I am coming to the very critical point, okay, going to a different domain. DSP and digital communication systems which demand highly pipelined and parallel architectures. Yesterday we discussed about this point. We have discussed with a small example where you want to do a parallel things, variety of things, where a processor thing cannot do. The FPGA is the best solution. High speed custom computing nodes. Today it is a very, today you talk about, I think you might have heard about these terms, what are called, custom computing nodes, okay. People talk about, whatever custom computing node is, it is a concept similar to supercomputer. Anybody knows what is a supercomputer? What is a supercomputer? It's a cluster of actually so many processors doing a thing. See, the concept is very simple. In supercomputer design, what we do, one single job, okay, single job means single application. We divide into, some small jobs. We see that each job is running on a different processor, which is high speed processor. So altogether I am able to use the power of 30 or 50 processors for doing one application. So I achieve high speed. That's the reason when you want to talk about very complex and high speed computations. Let's say, a rocket is going, okay. So you want to compute, the rocket direction and velocity and correct the motors. So there I may use some kind of supercomputer kind of thing. Okay, because I have to do in a very small time, as less time as I can do, that's a better, correct? So I'll use supercomputer because it does a lot of things in parallel by on several process do it. Exactly the same thing. When you say custom computing nodes, same thing. I have a very big complex computational task. Don't think computation means only I require, when I talk about the aircraft control or something. No. Today, computation is also involved when you talk about the simulation. Got the point? See, simulation means what? We design a model. Let's talk about, we are making a vehicle, okay, a four-wheeler kind of thing. Tata, the people, they design cars, okay, vehicles and all. We are talking about designing a vehicle, okay. So when you talk about designing the vehicle surface, okay, heat distribution on top of it, okay, how to control the heat distribution, okay, lot of things are required in it, okay. So there what we do, we make a mathematical model, okay, we simulate the model, okay, lot of computations we have to do. So there what we do generally, when you say complex simulation, it takes a general computer to run in hours, days also. I got the point. So there what we do, we make use of custom computing nodes if it is possible to design. If my application is a very repetitive application, I will call my hardware engineers, I'll ask them to design. This is a very complex mathematical algorithm. You design with maybe 30 processors or 40 processors and implement it. Even in those cases also, my FPGAs are the best suitable solutions because I can use one FPGA in that configure some 10-15 nodes which can do parallel jobs. Got the point or not? There. I can tell you another example. If you know anybody who are working in the real estate companies and all, generally what they do, they design some chip. Okay, so after designing the chip, generally they don't send it to fab directly because it's a very costly affair. Okay, they have to do a lot of analysis on it, whether it will work or not, whether it will meet the required dynamic characteristics, static characteristics. Okay, will it meet the power consumption? There are lot many chips which got failed because of inappropriate power heat distribution. So many chips. They come in the market, they work, only thing is the cooling mechanism or the heat distribution is not proper, so it won't work properly, after some time, so they will drop. These kind of chips, so many came in the market, okay. I can tell you one processor example, okay, this you may not be knowing, but don't worry, Motorola has released one processor, okay, with 7440 some architecture processor, the PowerPC processor. So one design is with 1 GHz, it's working well in the industry. They designed with 1.5 GHz on processor, slightly varied version. It came in the market, they manufactured it, it was working functionally, but only thing is inappropriate heat distribution. They could not dissipate the heat properly, so after some time the chip will start malfunctioning. Got the point or not? See, why it will malfunction? It will malfunction because, the moment temperature goes beyond some range, all my collector currents, everything will be going, so ones will become zeros, zeros will become ones, you don't know what will happen. You can't predict also. You got the point? Of course, now what they have done, they modified the design and they release a new process which is stable version, which is able to cater with that. So what I am trying to say, so once you are designing a chip, you have to do lot many analysis for it. So most of the VLSI engineers who design ASICs or who designed at the full custom level, okay, VLSI, what they do, they design it and they run they keep the simulation, okay, and they go home and come tomorrow morning, like, you know, it will take hours together to do simulation. So what I am trying to say, it is not only the onboard controller of a missile or aircraft requires high speed computation, okay, so many simulation techniques also need a lot of computation. So there also I will design custom computing nodes. Got the point? Now specific RISC-CISC network processor based applications. Okay, now here my interest is, I want to talk about what is a RISC and what is a CISC processor. Okay, anybody knows it? You might have studied in one subject called computer architecture and organization. Do you remember that subject? Yeah, I mean, anybody knows what is RISC? Yeah, RISC is reduced instruction set computer. Next, complex instruction set computer. Good, you are able to give the correct abbreviations. Now tell me, what do you mean by RISC and what do you mean by CISC? I mean, what will be the difference?
In this one command might take more than one clock cycle or something.
Okay.
They are complex, and this the commands are very simple. They mostly come in one clock cycle.
Few clock cycles, correct. That's one major important difference is the moment reduced instruction, the name itself is giving the meaning. Reduced instruction set computer, you mean there the number of instructions are reduced, okay, and the amount of job you are doing for one instruction is also reduced. Got the point? What I mean is, in a reduced instruction set computer, an instruction typically performs a small job in a very small amount of time. What do you mean by that? Maybe one clock cycle or two clock cycle, like that. Got the point? I think most of you studied 8085. Okay, 8085, 8086, this kind of process. Okay, there, you know, you have studied these words, if you remember: instruction cycle, machine cycle, T cycle. Remember the amount of, I mean, the one instruction cycle, you mean the time taken by one instruction for its execution. Not only time taken, we also talk about the amount of job done for executing one instruction. So one instruction cycle is having several machine cycles, and each machine cycle will have several T cycles. This is a scenario in the case of CISC, complex instruction set computer. In a complex instruction set computer, each instruction performs relatively a big job, a lengthy job, and it also takes actually a considerable amount of time, several tens of clock cycles, generally 18 clock cycles. What is a clock cycle? I mean, it's a CPU clock I am talking about. Okay, CPU clock, which we talk of 3 GHz or 4 GHz, like that. Okay, that's a different issue. A lot of other things are there, but let us be very simple at this point. Clock. So with that clock, RISC and CISC, the major difference is RISC will have less number of instructions, point number one, and each instruction does relatively a simple job with a very small amount of time, typically 2 clock cycles or 3 clock cycles. That's what the RISC. In CISC, I will have more number of instructions, so many instructions will be there. Got the point? So many varieties of instructions will be there, and each instruction performs relatively a lengthy job, okay, a complex job. Got the point? Example I can tell you. Let's say you have some kind of div instruction in some Intel processor, division. So division is a very lengthy job. Okay, it takes lot many clock cycles in it. Got the point? Okay, so I mean, this kind of instructions generally which are very lengthy and all, we don't design in RISC. We will give in different way. Okay, we understood the concept. RISC will have less number of instructions and each instruction takes less amount of time for execution. CISC will have more number of instructions and relatively each instruction takes a considerable amount of time, tens of clock cycles for execution. Good. Okay, then what's the advantage? Or why they have done like that? Or where it is suitable, where RISC is suitable and where RISC is suitable? Okay. Correct, very correct. See, RISC, reduced instruction set computer, because we are tailoring out the instruction set. We are making only 30 instructions or 20 instructions. That's all. Okay, so that is suitable wherever you have some applications, where you are going to do similar kind of job so many times. There are not many jobs. Like for example, if you take most of the DSP processors, they come with RISC architecture. Most of the DSP processors, Blackfin processor, Tiger, most of the processors, they are directly the RISC or the variants of the RISC, but ultimately they come into the RISC family of processors. You got the point? Most of the general purpose processors, you talk about the AMD Athlon processor or Intel P4 processor, they come with the CISC architecture. Okay, complex instructions. So wherever you require a general purpose application, wherever you are not very clear about the different varieties of small jobs, what I do, we go for CISC architecture. That's the reason most of the general purpose computers are made with the CISC. Got the point? But wherever I have a fine, refined, jobs, like, if you take the DSP, in the DSP case, we can shortlist, we can just say 15 operations are there, reading from RAM, writing from the RAM, very general things, it will be there anywhere, okay, Mac operation, okay, something like that I can easily make out and say 20 operations. These are 20 operations which I may do in a different sequence, in a variety of sequence, in a different manner, depending upon application, but ultimately I do 20 jobs only, usually. So come on, risky suitable for it. Got the point? So majority of the processors which are used in high end, what I should say, embedded application which cater for a very narrow areas, means there the number of small jobs are very less. Got the point? So majority of general purpose computers I create with the CISC architecture. But of course there is some kind of controversy. Intel claims that the P4 and the latest architectures are a combination of CISC and RISC. You get such kind of articles. You type in the internet, Google, Intel Pentium architecture, CISC, RISC, you get the articles, okay. So Intel claims the architecture is a combination of appropriate CISC and RISC, okay, and you get the, more perform, that's what they claim, but broadly speaking, we can say general purpose application, CISC is suitable, very fine application like a DSP and all, RISC is suitable, point number 1, okay. Now, yeah. Yeah, there is a difference. See, the point is, when you have a very small instruction set and each instruction takes a considerably small amount of time, the control to optimize the application is more in the hand of the programmer or the user. Got the point? See, when I have a very refined instruction set, each instruction got exactly fixed amount of time and I have only 20-30 instructions, so it is actually the programmer got more responsibility, programmer got more possibility to fine tune the application and get the best performance out of it. Okay, but when I have a CISC case, programmer is doing a small easy job. Programmer can tell in an easy way what to do, but the control to improve the performance is not much in his hand. It is already there, it is already absorbed in the design of the CISC. Got the point? Means if the CISC processor is appropriately designed, you will be able to get the best performance, otherwise you don't get it. Of course, that is true in the case of RISC processor also, but what I am trying, see, you can talk in this way. When you are using RISC processor, okay, so the programmer more effort will be required by the person who is developing the application, okay, and there is a possibility that he can fine tune the application to achieve the peak possible speeds on that. But when you talk about the CISC, the programmer generally takes a less burden, but you don't get that much of fine tuning, okay, on a CISC, okay. After some level, you can't improve the performance kind of thing on a CISC. That is the one thing. And second thing is, very important thing is, same application, same C code, okay, C code is 10 lines. I have used cross compiler, okay, for a RISC processor, case 1, case 2, I have used cross compiler for CISC processor, RISC, CISC. If you see the assembly code what is coming out, now I am asking this question to somebody, okay, now question to you, you tell me now, C code is same, 10 line C code, case 1 cross compiler for the RISC processor, okay, case 2 cross compiler for the CISC processor. Assume that we are talking about now the compiler job only to give up to the assembly equivalent of the C, isn't it? That's the first step. We know that when we compile something, first we get the assembly to C. You tell me now whether I get the lengthy assembly code in the case of RISC or lengthy assembly code in the case of CISC. In RISC we get it, obviously, in RISC. So what I want to say is, same amount of job, if you describe for a RISC processor, it will come as a lengthy assembly code. Okay, but the same job if you describe for the CISC processor, the code length will be less. Then it should be, according to you, RISC processor should take more amount of time for execution. Do you agree that? Because the assembly code is long, it takes more amount of time for execution. CISC assembly code is less, it takes less time. Do you agree that? Agree or not? You agreed? Think. What do you say?
But each instruction takes less amount of time.
See, it is not just, you can't say by how many assembly lines of coding is coming, isn't it? See, in a RISC case, each assembly instruction takes only 2 clock cycles or 3. In the CISC case, one assembly instruction may take 18 clock cycles, one may take only 4 clock cycles or like that. Okay, so I explained few properties. Now let us try to see inside, okay, of RISC and CISC, and let us also talk about where it is possible to improve the performance also. Okay. See, what happens in the case of design of the RISC processor, because all the instructions will have the similar execution time, same amount of execution time, 2 clock cycles or 3 clock cycles, it becomes very easy to improve the performance by the concept of pipelining, okay, by the concept of parallel execution units in ALU. I will repeat my point. What I am trying to say is, in the design, now I am going to the designer perspective. I told about actually when I'm using the RISC processor assembly code and all, that's a different issue. Now we are talking about designer perspective. When you are designing a RISC processor, it becomes easy, okay, for the designer to improve the speed, okay, in comparison with the CISC by some techniques. How and why? Let us discuss now. Okay, in the case of RISC, since each instruction takes relatively only 2 clock cycles or 3 clock cycles like that, okay, I mean it is almost similar. Okay, each instruction, almost all instructions take same amount of time. Okay, it becomes I mean it is easy for the designer to improve the performance. What do you mean speed? Okay, all this performance and all by implementing some concepts called pipelining. Most of you must have heard the word pipelining. Pipelining means what? You know, several execution elements are doing several jobs concurrently. Got the point? Let's say, you know, one instruction, the instruction fetch unit is fetching one instruction, the execution unit will be executing the instruction, the output unit will be appropriately updating the result registers with the output. So that is what concept of pipelining. Okay, do you have pipelining in 8085 microprocessor? That's my question. There is some level of pipelining in 8085 microprocessor, but that is not a pipelining at the ALU level. Actually, you know, in 8085 also some kind of pipelining is there, but that pipelining is only in terms of the read and execute cycles. You know, in 8085 is also, yes, some pipelining is there, but that is not visible to the programmer because that is purely at the hardware level. Okay, what I mean to say is, in 8085 also some kind of pipelining is there. Okay, when you are fetching one instruction from the external RAM, some portion of the execution of the previous instruction also will be done in that. But when you come to 8086, you see clearly, correct? In 8086 block diagram, you have seen there is a pipeline unit will be there, some pipeline stages will be there. That's what. Okay, so in all the modern processors, you have pipelines. You have pipelining in RISC, you have pipelining in CISC also. But the only thing is, in the case of RISC, pipelining will give the benefit in majority of the times in any kind of instruction sequence. But in the case of CISC, because I have one instruction which takes 4 clock cycles, I have one instruction which takes 30 clock cycles. See the point now. So even though I design some pipeline unit and all, the usage of the pipeline becomes less when you compare with the RISC. You got the point? It's a in-depth point, but what I want to say is the concepts like pipelining and parallel execution units, they become very useful in the case of RISC in comparison with the CISC case. CISC case, they follow different approaches to improve the speed. Okay, today both are giving high speeds, but when you talk about an embedded application, very specific application, we go for RISC. That's the more suitable. General purpose, we go for the CISC, that solution. Now let me also explain one more word which I used, parallel execution units. Anybody knows about it? Anybody can guess what are the parallel execution units? I can give you one important term which you can note down as a footnote in your notebook. Okay, today one very popular RISC architecture, okay, is PowerPC. I'm just only telling the word. Okay, we may not study in-depth aspects of it. I'm just telling the word and origin. Okay, so the PowerPC is architecture which is basically I think it's proposed by IBM, and later on it is used by most of the people. The architecture, it's an architecture, it's a CPU architecture, instruction set and all that. They said this kind of framework can give the more performance and all. PowerPC. So if you see what is the expansion of PowerPC, okay, performance enhancement through advanced RISC architecture, something like that. Maybe I may miss one or two lines like that. That is the idea. Okay, performance enhancement. I'm not very sure. You check that. Okay, you may just check it in the internet to get the appropriate. It is a one flavor of RISC basically. Okay, and why I am telling this point is I want to explain about the concurrent execution units. Okay, performance enhanced. Okay, advanced RISC. That's what. Okay, so now you see PowerPC. This is what. Now what I'm interested about PowerPC is PowerPC. You know, architecture. It got one concept. The concept is called superscalar execution units. This is what I want to explain. Okay, so PowerPC architecture, they have something called superscalar execution units in them, in their ALU or CPU, whatever you talk, ALU. Okay, what do you mean by that is there are parallel execution units for a different variety of requirements. Like you will have integer arithmetic will be there at one execution unit will be there. For floating point there will be separate execution unit will be there. You got the point? So when you say superscalar architecture, it will use the proper combination of the pipelining and parallel execution units to improve the speed. Got the point? That is also one type of RISC architecture. Today, most of the Motorola processors which are coming with the RISC architecture, they are PowerPC architecture. Okay, majority of the processors which are coming from the Motorola, okay, for embedded applications, they are with the PowerPC architecture. PowerPC is a very well-known family. Okay, people talk about PowerPC architecture, even in several applications. Got it? All are simple. Only thing is they slightly differ in the features in the hardware. If you know those features, you can use those features in the coding. You can improve your speed of the application. That's all. Okay. Got the point? I think by this time you got a very clear idea. Once I write a generic C code, the C code can be compiled for a P4 processor like my computer. It can be converted into appropriately assembly of my microcontroller. It can be implemented onto my PowerPC. It can be implemented onto ARM. Tomorrow you'll see it can be also put onto an FPGA also. Got the point? But only thing is where the engineering effort is coming into picture. If you know the special features in the processor or the controller, okay, you can make use of the special features in your coding and you can improve the speed. Without that also you can do it, but you don't get any benefits or you don't get the advantage of the architecture. Got the point? Okay. Yeah. Now last point. Okay, we discussed about RISC and CISC to some extent. Network processors. Anybody heard this one? At least can you guess where they will be? Huh? Correct. You are telling one feature what generally RISC processors do. But my question is, can you guess where they will be there? I mean, in which? No. See, a network system which may be having CDMA, there you may use it. But ultimately, when you say network processor, it is used in wherever the routers, the switches, wherever you talk about, there you have. Okay. So network processor is also something similar to, the way the general purpose processor is there. You derived a slight variation DSP processor. Network processor also has come like that only. Okay. In network processor, it is also a processor. There also the execution, instruction, everything is the same concept. But there the architecture is slightly tuned for networking applications. Okay. There in the processor itself you have some crossbar matrix where you can do the switching in it. Okay. So some network features are inbuilt in the processor. Okay. So today what you talk about the Cisco switches and all, the processors which are inside them all are actually of a network processor type. Got the point? Now why we are bringing all those things in the context of FPGA? That is, I want a general purpose processor, a RISC processor, and a network processor, a CAN controller, USB controller, Ethernet controller. All these things you don't get anywhere in a single chip. If you want to get, FPGA can do it. On FPGA, you write the VHDL code for it, or Verilog code or C code for it, put on a single FPGA, they will work all together. That's the concept. So altogether, whatever in a different way I explained throughout the slide, ultimately what I want to say is conclusions are very simple. FPGA where it is suitable. When I want to execute several things parallelly, okay, where generally my microprocessors and those cannot do, FPGA is the solution. Okay, when I want to reconfigure the system, where ASIC is very costly, FPGA can do this thing, isn't it? Where I have a variety of combination of the hardware, okay, CAN controller, bus controller, this, that and everything, like I want to get in a single chip, system on chip concept, FPGA can do the job. That's what. So I told so many other things actually, okay, which we are not talking about it. Okay. Now, so let us come to the issues which we discussed yesterday. What is the time now? Yeah. Okay. So we are going a bit slow. Okay. Yeah. Here I have just shown few, FPGAs and all. They are just the what you see from outside the chip is like this. Okay. This is what yesterday we have seen. Correct? We have seen this yesterday. Like, you will have what's called programmable interconnects. These are the interconnects, and the main thing which got the logic in it are called logic elements. Okay. Then what are other important blocks are IO blocks. Okay, they are IO blocks. Basically, these IO blocks, they have a lot of control in it. You can even program to an extent that how much of current drive should come from that pin. Also, you can configure. You can configure one pin as an input pin or output pin. Okay, you can configure the pin to give either TTL voltage levels or a CMOS levels. Okay, lot of things are possible. Okay, that's what. Yeah, that's only. See, simple. The point is, when I say routing channel, it is a wire which is coming this. When I say programmable interconnect, it is some matrix. Okay, where you are connecting those wires with some switches. That's what. We did not discuss in that way yesterday. Yesterday we said programmable interconnects. Okay, so programmable interconnect, when you say, it is basically a kind of matrix where I have lot many MOSFETs kind of thing, where I can program those connections. Routing channel, what I mean, the wires which are running between the various programs. So routing wire channels are only just wires. That's all. And programmable interconnects are those pieces where you are connecting the wires, routing channels appropriately. isn't it? What I mean appropriate, I am writing some piece of logic where the output of this logic element should go to the input of it. So I'll program this way. I will show that. Okay, I will show those things in Spartan 3 inside view. Okay. Now this is what we have seen yesterday. Yesterday I have drawn a rough diagram. This is what you are seeing. This is from the Xilinx one FPGA. The FPGA number is here. So as I said yesterday, the Xilinx calls this one as one configurable logic block. So this is what. So you will have lookup tables. So this is what yesterday I have told. Generally, today's most of the FPGAs, they come with 2 4-input lookup tables and 1 2-input lookup table. That's what. Okay. Now they got lot many multiplexers and all. Okay. So they have generally 1 or 2 flip-flops, because when you want to implement sequential logic, they require it. But of course, it is not as shown in this diagram. You require so many places the programmable interconnects. Okay. Programmable switches or fuses, what you talk of, isn't it? It is not just like all the connections what are shown here. At every point, you'll have some switch like that. Okay. So nothing new, because yesterday we discussed about all this, we know it. Yeah. So now I want to say, like the way you know how to develop embedded system on a microcontroller or a microprocessor, means you are generating some X file, programming into the flash. What is its scenario in the case of FPGA? We are talking about it. So we use a word called synthesis, correct? Okay, FPGA synthesis. Okay. So what do you mean by synthesis? The idea is, let's take a small example. Okay, this is the logic what you want to implement. This you can explain through VHDL code or Verilog code or a C code, by any way, whatever you want, you can tell. Okay. Now the tool, what it does, it translates that synthesis into a bit file. Okay, which ultimately maps one lookup table to realize this logic. Got the point? So in the case of FPGA, what ultimately you mean by synthesis? What exactly you are doing is, how do we map the functionality into some logic elements or the blocks inside the logic elements, mean lookup tables and multiplexers? How do we implement an operation within a logic element? So within a multiplexer, how you are programming them? First thing is, bigger logic, you are partitioning into different logic elements. Within a logic element, how you are keeping fuses and connections to implement your logic. And third one is, how do we program the interconnects to make all the connections done and the input outputs are coming to the chip pins. That is only the FPGA synthesis. That's all. Correct or not? Okay. So these words I have taken from that reference book which I told earlier. FPGA based system design by Wolf, WOLF, Wolf. Okay. I can suggest you can go to this website, www.princeton.edu. Okay, go to this link. Is it correct slash what I used or reverse? Correct, na? Okay. Sorry. Wolf. Okay. So go to this page. Okay. He's a big man. Actually, he has done a lot of research on system on chip, embedded system and all. You explore all the links which are given there. Okay. All the links. He gives books, articles. Okay. His presentations, papers and all. Explore. Okay. You will find some relevant information. Okay. But definitely, whatever he talks, you cannot understand. But at least we'll understand his introduction, what he's trying to say. System on chip, this, that concept, hardware, software, code design, many things are given there. Okay. His presentations, his papers, IT papers, everything is there. There, you will find, if you open this page, there one books tab will be there. If you go to that, FPGA based system design tab will be there. Okay. If you go in that, of course you don't give the book because that book is selling outside. It costs around 200 or 300. FPGA based system design by Wolf book. Whatever the handouts and diagrams you are used in it, those all presentations are there. Presentations, some notes are there. You can make use of it. Okay. You can get some idea about it, but that book is worth of reading. If you are interested in this line, a complex embedded system designed by FPGAs and all, you are interested in this line, that book is a good book, you can read it. It's a very simple book. At least the first 4 or 5 chapters, happily you can read by your own, without knowing anything. Okay. But since we are also giving the introduction to ISE, Embedded Development Kit, you will definitely able to follow the complete book. Okay. That's a very good book. That's a beginner's book, I should say, for FPGA. Okay. Yeah. Now, so I'm going a bit into different FPGA technologies. Okay, like he might have told, microcontrollers, some microcontrollers come with inbuilt flash, some come with like this different variations. FPGAs also come with a different flavors. Okay, SRAM based FPGA. Okay, so the idea is what? SRAM, anybody knows what is SRAM? Static RAM, isn't it? It is one type of RAM. It is one type of read-write memory. Okay, static RAM. Now another type of FPGA, they are called anti-fuse based FPGA. Another type of FPGA, they are called flash based FPGA. Of course, you have fuse based FPGA also, but okay, fuse based and anti-fuse based, they are only technology wise they're different. I mean, features wise both give the same features, fuse and anti-fuse. We'll talk about it. Okay. Now, what we are trying to say? What are all these things? If you see, these are the different ways you put the bit file in the FPGA. That's all. Okay. SRAM based FPGA, and see, we are not talking in the sense of the architecture of logic cells. Okay, we are not talking in the sense of the kind of routing mechanism. No, we are talking only in the sense, in the context, how the bit file is being programmed into the FPGA. Okay, whether that is placed temporarily into the SRAM inside the FPGA, if it is SRAM based FPGA, if it is flash based FPGA, the bit file is programmed into the flash, so it becomes non-volatile, like that. So we are looking at that option. We'll discuss now, don't worry. Okay, so SRAM based FPGA, as you know, SRAM is volatile and it is reprogrammable. You know that? SRAM is volatile and it is reprogrammable. Any number of times you can read and write and all that. Okay, so they can be programmed many times. The main advantage of SRAM based FPGA. Okay, SRAM must be programmed at power up, otherwise it won't work. Because when you power on, if you are using SRAM based FPGA, it expects that from SRAM it loads the bit file and connects all the, gives the inputs to the MOSFET gates and all. Okay, if it is anti-fuse based, fuse based and anti-fuse based, the concept is very, very simple. Yesterday somebody was asking what is fuse and anti-fuse. It is quite similar to the fuse concept what we use in our household applications for electric supplies and all. See, what is the concept in our electric fuse? Can I ask you? No, my question is, see, all in our houses, we put fuse at the mains, correct? It is doing some job. How it works, No, it passes current, but basically what is its main job? What is the main function of fuse? I'm talking about this fuse. If current exceeds a certain value, it opens. It opens circuit. How it opens? The wire melts. The wire, it melts after all. It melts, isn't it? It melts. Okay. Of course, we talk, the fuse got blown, but ultimately what's happening? It melts. But how it melts? The type of material what we use for making that fuse will have, lesser melting temperature and all. So you know that H is equal to I square RT by J equation. So when I amount of current is flowing through some material which got R amount of resistance, you can calculate that heat. Okay, you can convert that in temperature, isn't it? So that is exactly the principle. So when the current goes one limit, the heat value is in such a way that the wire melts. Okay, that's what. So that's why it is a wrong concept if you put a bigger wire for fuse and say that my fuse will never blow. If your fuse will blow, your electrical equipment will go bad. Okay, so better you keep a fuse which blows with appropriate current rating, isn't it? So fuses are very critical. Okay, if you make a fuse which is not blown, which is not blowing, means your electric circuit will blow. The applications. Okay, so quite similar to that. Even in our all our fuse based concepts, CPLDs and FPGAs and all, wherever you say fuse technology, quite similar. Yesterday also I talked about PROM. I talked about the fuse. That's the same concept. Okay, what is the concept? There also you have some kind of material by giving some amount of, but not this much of large current. Okay, so maybe 30 amperes at 25 amperes, I can blow the fuse. So there also exactly same concept. But only thing what we do is we use the decoders and all, so that we can route that current to appropriate fuses where we want to blow, because we have so many fuses now. That's it. Anti-fuse is the opposite concept of it. What is opposite? Fuse means by default it is a closed circuit. When I want to open, I have to give high amount of current. Anti-fuse is the reverse. By default it is an open circuit. When I want to make the connection, I have to give high amount of electric fields, like that. Got the point? We will see that. Now other one is a flash. Today we are using flash, in a variety of ways, isn't it? All your cards which are coming, your camera phones, mobiles, 1 GB card, what you talk, they are all flash memories only. Okay, pen drive, what you use, they are all flash technology. Okay, so flash got the advantages of both fuse and SRAM. Can anybody tell? Flash got the advantages of both with the SRAM and fuse. The point is, flash is one way reprogrammable. You can program any number of times, and it is permanent also. If you remove the power, again you power on, so it works, but it is reprogrammable. But you don't have these two together in the fuse and SRAM. SRAM is reprogrammable, but by power on, you have to load every time the bit file. Fuse is not reprogrammable, but once you load something, you cannot change it. Flash got both the things. Okay, you will see now one by one. This is what yesterday I was trying to explain. Okay, when you say SRAM based FPGA, after all, what is happening? There is, of course, not like each SRAM for each bit, like what yesterday I have shown. There will be one SRAM. Okay, from SRAM each bit there will be connections to so many MOSFETs in the FPGA. Okay, I mean, it is not that every one SRAM will be there for one MOSFET. Okay, there is a big SRAM will be there. Each SRAM output will go to one gate, one MOSFET gate. Now, depending upon whether you store in that bit 1 or 0, okay, that MOSFET will be closed or open. Now, for example, you have implemented such a logic where these two need to be shorted. Okay, so an SRAM bit will be 1. That is what exactly my tools will do. When I give some VHDL code and when I say Spartan 3 FPGA, it knows how to configure the Spartan 3 FPGA. In Spartan 3 FPGA, which MOSFET to open, which MOSFET to close to realize the logic. That is what exactly the job done in the synthesis tools. Got the point? Okay. Now this is what SRAM. I think very simple to understand SRAM based FPGA. Because I am using SRAM which is non-volatile, my SRAM based FPGA is non-volatile and it is reprogrammable. That's all. Anti-fuse. See the concept of anti-fuse based FPGA. Okay, in anti-fuse based FPGA, as you can see here, okay, you see now, in anti-fuse FPGA, I have something called N plus diffusion, which is like a metal. You might have studied this like in your MOSFET concept, wherever you heavily doped N region, heavily doped, they are considered to be equivalent of metals. Okay, so this is like one conductor. See now, this is like one conductor. The topper layer is a polysilicon. People who studied the VLSI, they know that polysilicon is used instead of metal because it got more adhesiveness towards silicon. So because polysilicon sits on a better way on silicon than metal, so we use polysilicon to do a lot of the job like a metal what is supposed to do on silicon, isn't it? All your MOSFET gates and all we do by only polysilicon. Okay, so concept is you have one conductor here, look at this, another conductor here. Okay, in between there is what is this? Dielectric. This white color one is a dielectric. So by giving the appropriate amount of electric field, we puncture through the dielectric, so it is programmed. So it is also similar to the anti-fuse. But the point is here by default there is open circuit, you can make a closed circuit. But this is also programmable only once. You cannot program several times. Got the point? Once the dielectric got punctured through, okay, and once the connection is made, that's all. You cannot again reverse it. Of course, what I exactly shown, it is one company Actel. Actel is also a big company, they make lot many FPGAs. Okay, Actel FPGAs are known, Actel flash based FPGAs are more known than Xilinx and Altera solutions. Means they are more experts in making permanent programmable FPGAs. Okay, but Altera and Xilinx, they give good FPGAs which are based upon SRAM. Okay, yeah, now a comparison is given. I think all of us we convinced with these things what are given. If it is fuse based, it is not reprogrammable, correct? Only once. If it is EEPROM based, now certain things which are not told also given here. EEPROM and EEPROM all of you know. EEPROM concept is what? It is also programmable, but you need to erase through ultraviolet rays and all, some mechanism. But today you are not talking about, today you are not getting EEPROM and EEPROM based. Today you find in the market SRAM based FPGA, flash based FPGAs. That's all. And anti-fuse based FPGA. That's what. Okay, three varieties. SRAM, okay, anti-fuse, flash. SRAM is something where you are only using in R&D purpose. You never want to make the program permanent on it. Anti-fuse is something you want to permanently program once, that's all. Flash is something which got the advantages of both. That's the reason obviously the flash based FPGAs are costlier. Okay, that's all. So now SRAM, EEPROM, they are all yes, but in case of EEPROM, the erasing mechanism is out of circuit because I have to leave it. In case of EEPROM and SRAM, I need not disturb the FPGA, there itself I can erase and put a new file, isn't it? Now volatile, yes. This is volatile, this is non-volatile, SRAM base is volatile and anti-fuse is also non-volatile, correct? I think in this flash is missing, correct? Sorry, flash I did not give. I can, all of you can understand. You can also add one more row bottom, okay? If it is flash, tell me reprogrammability yes or no? Yes. In case of flash, it is reprogrammability yes, okay? And that is out, that is in circuit only. In case of flash, okay? And volatile? No. Flash is non-volatile. Means even if you remove the power, the contents are still there. If you again give the power, it works. Okay. And in case of flash, I am not sure what is the technology. Okay. That you can search in the internet. Technology, what do you mean? Whether it is which kind of logic families are used to implement it? I'm not sure because there are varieties of flavors are available. Exactly in FPGA context, flash how they are made, I don't know. Okay. You can search in the internet. Okay. Now let us come out of the in-depth discussion and talk superficially. FPGA based embedded systems, how they can be implemented. See, FPGA based embedded system can be implemented by using any one of the following languages. You can use a VHDL or Verilog. Why I have put those two into one category? They are understood as a standard hardware description languages. VHDL, Verilog. Okay. Of course, System C is also hardware description language, but the other languages like System C, System Verilog, they are all considered to be at the higher abstraction level than hardware description languages. See, VHDL Verilog, they allow you to do it actually what is called register level and all that level of coding, okay. But in system to system Verilog, most of the times we write the superficially code, okay. See, system Verilog is something, it is somewhat similar to the C++ kind of thing. We go by object oriented mechanism. We talk in a high in a superficial way. We don't talk at the register level and all. But in VHDL Verilog, when you do, you are working at slightly at the lower level. That's why they are in a different manner, they are in a different manner. You know, today in industry both are used. VHDL Verilog, they are used, you know, directly when you are implementing the logic on the chip. Tomorrow you may go for ASIC or FPGA, you will use VHDL Verilog. But let's say I am writing some hardware description language which is not meant for implementing, which is meant for verification of some other logic, or you know, some other verification or test bench kind of thing, then I will use system Verilog or system C. Got the point? So today system Verilog is very, very popular in the testing perspective. There are so many job opportunities in Indian industry, you know, if you are good in testing. Only if you know how to testing VHDL Verilog code using model sim is also fantastic. You'll get a lot of salaries. Got the point? So tomorrow afternoon 1 to 3 o'clock session will be based upon model sim and Xilinx ASC. So you pay full attention towards it. It is about fully tool session. Okay, tool oriented. Even though for some of VLSI guys I have given model sim view, but tomorrow it's a fully dedicated tool orientation. Got it? So what I'm trying to say is, you got my point? When you are implementing the actual logic, tomorrow either you are going for ASIC or you know FPGA, if it is the actual logic which has to run on the chip, we prefer VHDL Verilog kind of thing, because there the efficiency when you do synthesis and all, getting more speeds, getting less, you know, less chip silicon area, that is possible. But when you are writing some hardware description language code which is only meant for verifying some other hardware description language module or something, I may prefer even simpler way of doing it, like system Verilog or system C, like that. Got the point? Next, see this point, fantastic. Assembly language compatible with a chosen soft processor cores. Example, I told microcontroller, but even microprocessor is also soft processor. Okay. Now let me explain the word. What do you mean soft processor? What do you mean hard processor? Anybody can tell about this? Let's say I have a FPGA. I'm holding an FPGA. When I say this FPGA got a hard 32-bit RISC processor, what do you mean? This FPGA can have a you know, soft 32-bit microprocessor. What do you mean? Can anybody can guess? Exactly. Hard processor means it is implemented already in the processor, okay, at the silicon level, at the layout level it is implemented. Got the point or not? So when you say hard processor, what you mean is, see, generally we don't talk hard processor, soft processor in the context of microprocessor, because in the case of microprocessor everything is hard. Everything is hard. There is nothing like soft, isn't it? But in the case of actually, you know, FPGAs, we do talk these two words, hard processor and soft processor. When you say hard processor on FPGA, hard core, what you mean is the actual chip, the processor is implemented at the silicon level. It is available as if it is like your general purpose processor, which is a part in the FPGA, which is somewhere at one place of the FPGA. When you say soft processor, what do you mean? You are writing the VHDL code for the processor, which will sit on top of the FPGA, and on top of that you put the assembly code or the C code, which is going to do the job. So today people design FPGA based embedded systems using both hard processors and soft processors. This is exactly where the word hardware and software co-design comes into picture. You got the point? Now I'll tell you what is hardware software co-design, especially in the FPGA perspective is, imagine I have an FPGA. FPGA got, let's say, one hard processor, or I may use one soft processor. On top of that I am writing some software, isn't it? See, whenever I write a sequential C code or assembly code, you know, we call it as a pure software, isn't it? So I am designing some portion of my system in terms of software. Just side by, isn't it? In the same FPGA, just side by my processor, maybe hard processor, soft processor, I have logic cells also. Okay, I have logic cells also. I am writing my VHDL code or Verilog code to implement some hardware logic in the logic cells. You see now, I am doing hardware and software together. This is what we make hardware and software co-design. Got the point? So tomorrow, whatever Kumar sir is going to take from 3 to 5, okay, that is embedded development kit. That is what actually, I mean, an example. I don't say that itself is one thing. That is a tool from Xilinx. That is an example what people are using for hardware and software co-design. Got the point? Are you clear? See, what I'm trying to say is, you are writing some portion of the VHDL code. Acha, people who are not attended for the VHDL session, I want to give one important concept to them. VHDL code, Verilog code, how they are different than conventional C codes and all. At least my VLSI team people should give the answer. Main thing is, VHDL code and Verilog codes, they are concurrent in nature. Okay, by default when I write a VHDL code 10 lines are running parallelly. What do you mean by that? When I implement in FPGA, all the 10 lines will be implemented parallelly on a different piece of hardware. Got the point? But when I write a conventional C code or assembly code, what they generally do, they execute one after another, sequential. That's why, I'll again repeat my concept of what is called hardware software co-design. Imagine a case, FPGA. On FPGA, either I have a soft processor or a hard processor. Okay, something I have. For that processor, what I am doing, I am writing some C code or assembly code. This is software part of it. Second thing. On the same FPGA, along with the processor, I have so many logic cells and all those things. So I am writing some portion of the VHDL code, Verilog code, to configure the FPGA logic cells to do some job, which is somewhat similar to the hardware design, hardware reconfiguration of FPGA. So when you do all this together to work as a single system in one FPGA, we call it as hardware software co-design. But of course, people also talk like, when I am doing an FPGA some hardware design, a DSP processor one software design, put these two together on a board, PCB, that is also called hardware software co-design. But when you talk at silicon level, chip level, hardware software co-design means exactly this one. In FPGA context, hardware co-design is exactly this one. Okay, if you are interested, just type in the internet hardware software co-design in FPGA, you will get some basic idea. Yeah. So what is the last one? You can as well use some high level languages. Why only assembly? If I have a processor, I can also write a C code, and I can use a cross compiler which is converting the C code to the appropriate assembly or C. Okay. Now this is the main diagram which should fit in your mind to differentiate what is a general embedded system, what is an FPGA based embedded system, especially in hardware software perspective. Okay, if I am using an FPGA, I am writing some C code, means something like this is happening. What do you mean by it? Let's see. In conventional embedded system, I will have the hardware which is generally hard implementation. Okay, no software issue. Okay, it is definitely hard implementation, processor or microcontroller. Then optionally I may have a kernel or operating system. I think embedded system people will appreciate this. Some embedded systems can be there with kernel or some without kernel. The example what you have seen 2 days before with microcontroller serial port programming, is it having kernel or is running without kernel? Without kernel, isn't it? See, when I am writing only one thread, one application where I don't need a kernel kind of thing, I don't have it. But when I am writing some embedded system, when I am designing where multiple threads are there, memory management is required, resource management is required, I'll optionally go for kernel, isn't it? That's what. Now what is the next one? Application program. So on top of kernel, application program will run. But if you look at the FPGA based system, everything is same, but the point is one more layer is coming into picture. Okay, either I may use, let's say if FPGA itself is not hard processor, it's a different issue. It is quite similar to what you are doing it. Okay, but if you are doing by soft processor, on top of FPGA, on top of FPGA we have processor code, processor VHDL code or Verilog code or some other code. On top of that we have, what is it called, kernel, optionally, that is also, and on top of that we have application. That's what. Okay, this is an example of a 8-bit microcontroller code which is from Xilinx. The code is also available freely, you can download and you can see the code. It's a pure VHDL code, Verilog codes are given for it. Okay, you can see it. This is what 8-bit microcontroller. It is somewhat similar to the microcontrollers. It will also have lot many register sets, okay, lot many port controls and so many things actually. Quite similar to a general purpose microcontroller, but the idea is what? It is a soft microcontroller. The VHDL code or Verilog code I can use, I can build along with the application, put onto FPGA. Now you will see a typical example. Okay, this is a board which we are going to try out. Tomorrow he is going to give one example, and day after tomorrow onwards we are going to run with this board only. Okay, now this is a small example, I'll skip time being. Now let us come to this point now. See, I am showing a typical scenario. This is my top level VHDL module. Okay, this top level VHDL module got one component. That component is what? This is a not this. This is actually the user constraint file. I think some of you can understand. For whom I discussed actually the user constraint file and all. Tomorrow you will come to know what user constraint file is. See, you are writing some code which is running inside the FPGA, but its inputs and outputs has to be brought to some pins of the FPGA, so they are called pin constraints. Okay, see, you want to optimize one specific one path which you felt critical path, that has to be given highest priority to improve the speed. So that is what called timing constraints. So pin constraints, timing constraints, area constraints, all these things we give in a form called user constraint file. UCF file. Okay, so that is a UCF file. And see, this is what my PicoBlaze code, okay, which is in the color green color, PicoBlaze processor for Spartan 3 devices. This is what the code, VHDL code. Okay, if maybe today is we don't have time, we'll see in the next class, maybe on Monday with an example. But tomorrow you are going to get an example with a microblaze, which is also similar, but it's a bigger one. It is a 32-bit microprocessor. This is a 8-bit microcontroller, very small thing. Okay, but microcontroller VHDL code or Verilog code is not given freely in the internet. No, They don't give the Visual Code Verilog code, but they give their lower versions of it, means their netlist. Whatever you get like compiling after that one they'll give. They don't give the code of it, source code of it. Okay, you have to purchase it. I think it costs around $5,000 or something like. If you want to purchase the Microblaze code, original source code. But PicoBlaze is a good example to work with. We'll work from Monday onwards. Okay. Now you see how this is going to work. I have basically one assembly program. See, this is a PicoBlaze program, assembly code. This assembly code I compile, something similar to the cross compiler. I generate the VHDL module. What is the VHDL module? This is just like a ROM, read-only memory, which is having the mission code of my program, isn't it? Isn't it how basically your microprocessor working? It will have externally ROM or RAM where you get the instruction and keep execute. In a similar way, here also my soft processor core will keep and execute the instruction and execute that. That instruction, that mission code is coming from where? That is coming from your when you assemble your assembly code, you get a VHDL file. That VHDL file will have it. I'll show all these things on Monday. Okay, let me just keep it. So these are some important articles. I'm sorry. Okay. Is there? Just let me take few minutes. Okay. I will show. If some of you are getting delayed, you can go. Okay, because this portion of the topic I am going to again repeat anyhow. Sorry. I want to change the date because the time, okay, for which my Xilinx ISC evaluation works is over. It's not responding. Let me see whether it opens or not. Tomorrow you are going to have an in-depth talk about this tool. Okay, so this tool will allow you to, like the similar way, the Microblaze, what is that IDE? Keel IDE, Microvision IDE, quite similar to that. This is for FPGA based thing, especially given by Xilinx for their own FPGAs. But it is possible to put a variety of tools in it. Okay, it is possible to put a variety of synthesizers and simulators in it. Okay. This okay. Internet is not there. Now I just want to show what is a Spartan 3 inside CLB looks like. Okay. Because yesterday I told I'll show the Spartan 3 inside. Let me just see. No, not this. View, edit, rooted design. I don't know whether it opens or says evaluation date out, or let me see. So see, like logic cell concept, what you have seen is a fundamental. But today's modern FPGAs, they come with different ways. Like if you see Spartan 3 FPGA, that is going to have one CLB 4 slices. Okay, each slice will have like what you have seen in the block, like 2 lookup tables and all. Okay, that's how they manage. They call slice 4 slices. Okay, now this, let's see this. So this is how once you see the FPGA inside, it looks like this way. Okay, let me zoom inside. What is this? Zoom area. Yeah. See now, this is what you had seen. This is one slice, slice, slice. Okay, and this box, big box, what you are seeing here, it is basically the matrix where all programmable connections are there. Now you are seeing it some portion of the chip which is not used by the design. So I will take you some portion where it is used. Okay, you will see all the connections and switch matrix. Let me come out of it. Yeah, this is somewhere where I am using the chip. So let me take you there. So whatever you are seeing, basically it is called floor plan. Okay. Okay, now you see there is some significance for the color, what for it is using it, that we will discuss later. But have a look at this piece, what I am trying to show now. So all these 4 put together, they are called one CLB in Spartan 3 FPGA. Okay, each CLB will all these 4 together called CLB. Each one is called one slice. See, the moment I put a mouse there, it is showing slice X47, Y81. They are designated by generally the row number and column number. Okay. What is inside of each slice I will show now. Okay. But you look at this now, some of you ask like, what is the routing interconnection, programmable interconnect kind of thing. Now you see, sorry, I missed it. Okay, here also I can show. See, you see this kind of a box is there, you see. In this box, so many wires are moving from this end to that end. Okay. So this is basically called a switch matrix for one CLB. Each CLB you are seeing side by there is a switch matrix. So what that is doing is, if the logic is implemented within the slices, from this slide to that slide, this slice, all interconnection, from this complete CLB to next CLB, all the routing is done. So if you can see, some of the wires which are coming from here, it is going to a different CLB, like this. Got the point? So this is what basically, one thing looks like. I think, can I go inside by double clicking? No, it won't allow here. Okay, give me 1 second. So this is the data sheet of the Spartan 3 family FPGA. Okay, I will take you to one place where he talks about the CLBs inside. See now, configurable logic block and slice. Okay, let me say full screen. Okay, now you watch. Okay, this one. This is what is shown. Each Spartan 3 FPGA will be divided into some CLBs. Each CLB will have 4 slices. That's what is shown. Now he'll show you what is inside a slice. Now look at this, what inside a slice. Okay, is it quite similar to what you have seen yesterday? You may not be able to see the things very clearly, but you'll get the basic idea. You see now, I think you can see this is a lookup table. This is also a lookup table. Okay, and so many multiplexers are there. Of course, you are seeing some XOR gates and all. They are mainly for implementing the fast carry chains and all that. Okay, you are seeing 2 flip-flops. This is what inside one slice. Okay, like this 4 slices put together along with the switch matrix. This is called one CLB. This is what you see now. This is what the architecture. Let me just maximize this. See this now. Yeah. See 4 slices and there is a switch matrix together. Okay, and this is the connection which is to all other interconnects and all. So this is giving switch matrix is doing the most of the interconnects between the slices and all. So these are basically the Spartan 3 CLB is configured. So every FPGA got like this its own architecture, its own connection mechanism and all that. Okay, but once it is coming in the same family, Spartan 3 FPGA, whether it is a different version, they have similar architecture like that. Spartan 2 family, if you see, each CLB will have 2 slices like that. So different architecture. Okay, Altera follows a completely different nomenclature and different architecture and everything. So we shall see some examples. Okay, so let us meet. So tomorrow you are coming at afternoon 1 o'clock. Okay, and you will be staying up to 5 or 5:30. There will be breaks, of course, in between. Okay. So he talks about, you see, Spartan 3 FPGA got dedicated multipliers. Okay, dedicated multipliers, their connections, lot of things are there. So generally, when you are trying to develop embedded system very seriously to optimize its performance and everything, okay, we try to understand the architecture of the FPGA, and in our constraints, okay, area constraints and all, appropriately I will make use of the resources in the FPGA. Like for example, I need a multiplier. I will map the multiplier into the hard multiplier which is there in the FPGA. So I get a high speed like that. Okay. Okay. So I am coming again on Monday.